Now we will see the material related to alternating series and absolute convergence. This material is normally very easy and straightforward, so it's not going to be that difficult. This is here just a slide with some reminders that could be useful later on of some inequalities that we might use. So it's good to have kind of reminder sheet. In our studies, we up to now have seen only series with positive general term. Now we are going to see some series that have alternating signs. So one term is positive, the other one is negative, or one is negative, the other one is positive in a sequence. And also we are going to see some series that have some mixed terms with mixed signs and see what we can do there. So first we start with alternating series. What is the alternating series? It is a series whose terms change sign consecutively. So you see here two examples. Here in the first example, the first term is positive, then the second is negative. Third term is positive, then the next is negative, positive, negative, positive, negative, and it keeps going like that. Two consecutive terms always have different sign. So general expression would be something similar to this. So you have 1 over n, so 1 over 1, 1 over 2, 1 over 3, 1 over 4. And then this term here is responsible for the sign. So minus 1, n to power n minus 1. Sometimes you will have minus 1 to power n, sometimes minus 1 to power n plus 1, depending on the situation. But this term here with negative 1 to some power, that's the term that is responsible for the sign. And the general term, the expression here is given next. Now, in another example, here we start with a negative sign, then the next sign is positive, then negative, positive, negative, positive. So what matters here again is that any two consecutive terms have different sign. So positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive. So that's what makes a series alternating. So the sign is alternating consecutively. So that's an important thing. Obviously, if we take an absolute value of the expression, well, we'll get only the positive part. That's normal. So that's nothing special there. So again, the important thing with alternating series is this negative 1 to some power. You see here k plus 1. So when k is 1, k plus 1 is 2, so minus 1 to power 2 is 1. So that's why our first term is positive. Then the next one will be negative, then positive, then negative. So signs are alternating immediately one after the other. It's important to distinguish that from other types of series. So the alternating series have these consecutive terms that change sign immediately. Some other series have mixed positive and negative terms, but they are not changing one after the other. So one example here, you have a series that turns out to be convergent, but where you have positive, positive, then negative, then positive, positive, negative, positive, positive, negative. So technically this is not an alternating series, because alternating series would change signs after each term. But here you have two positives, then one negative, two positives, then one negative. So this is not alternating at all. So we will need tools to determine convergence of such series also, but those are completely different tools. Another example here is with cosine or sine n divided by n squared, for instance. So cosine will change signs. It will be sometimes positive, sometimes negative, but irregularly. It's not going to be after each consecutive term. So this series is not alternating. So it's important just to realize that some series do change sign each term one after the other. So those are alternating. And some other series, they do have positive and negative terms, but the change is not systematic one after the other. So this is not alternating, this is not alternating. It's just important to distinguish, because the tool to determine the convergence of alternating series is called alternating series test, and it's very easy to use. Actually, we need to check two conditions. First condition is that the next term is smaller than the previous. So we have the change of sign and then the expression. Normally this expression here is positive, the B, and then we just compare the next term and the current term. Normally we would like to have it for all n, so from n 1, 2, 3, 4, but it's not necessary. Sometimes we can have this condition satisfied for n bigger than 4, for instance. That's fine also. There's no issue there. And another condition is that the general term, the positive part, is converging to 0. So with these two conditions, we can conclude immediately that the alternating series is convergent. So it's important to realize that this tool is very simple to use, but also that we need to know when the series is alternating and when it's not. So the easy thing is to check the -1 to some power to see the change of sign, and then we check these two conditions. You recognize these conditions from before. The general term needs to go to 0. If it doesn't, the series is divergent by divergence test. So that's something that needs to happen for all series. The general term needs to go to 0. If it doesn't, then we can use divergence test to conclude that the series is divergent. However, this part here is required for the alternating series. Now, if this is not satisfied, the first condition, we cannot use the alternating series test. That's all it means. We cannot use it. Maybe we can use some other test to check the convergence. So it's important to realize that alternating series, the test is very simple, but this is test for convergence. Okay? When both of these conditions are satisfied, for the alternating series, we conclude that the alternating series is convergent. So we must check both conditions at the same time. Also, as we said, this is a convergence test. So when both conditions are satisfied, we will conclude that the alternating series is convergent. However, if the condition here of the greater or equal, so the next term is smaller than the previous, if that one is not satisfied, we cannot conclude anything. We just cannot use the test. That's all. So even though the general term goes to 0, if this condition is not satisfied, we cannot use the alternating series test. So alternating series test is only useful for the alternating series and when both conditions are satisfied. Obviously, as we said, if the general term is not going to 0, if the limit is not 0, then by divergence test, we know that the series is divergent. In that case, obviously, the series with the positive terms would be divergent, but also series that is alternating will be divergent also, just because the general term is not going to 0. Okay, so that's important. Also, the alternating series test is valid only for alternating series. So if we have a series like here that has mixed signs, but it's not alternating actually, well, there is no point of trying to apply the alternating series test because this series is not alternating series. So we don't apply the test for alternating series on something that is not alternating. Okay? So it's important just to distinguish that. We will see how we got that this series is actually convergent to some number. And also this series will be convergent using another tool, but not tool for alternating series because this series here is not alternating. So just need to be clear on that because we need to use appropriate tool for the correct series. One of the series that we have seen before is harmonic series, and we know already that that series is divergent. However, we have an alternating version, so where the signs are changing. So this is called alternating harmonic. So you see positive sign, positive, negative. Now, this is an alternating series. the general term is 1 over n. So let's check the two conditions. The easy one is to check the limit of 1 over n. Obviously that's 0, so one condition is satisfied. And now the second condition is to see if the next term is smaller than the current term. Well, that's easy, it's straightforward. 1 over n plus 1 is obviously smaller than 1 over n. So in many cases, verification of these two conditions will be straightforward, but we still need to write it down. So since both conditions for alternating series are satisfied, this original alternating series is convergent by alternating series test. So you see the application is very easy. Most of the time these checks are very simple and straightforward. We will see some cases where we need some more work also. So we know that harmonic series in itself is divergent. However, we just now proved that alternating harmonic series is convergent. Now we don't know what's the value of the sum. Later on we will discover that the value of the sum of alternating harmonic series is ln2. For now we don't know how. We will see that later on. However, we could obviously find an approximation for a sum by adding certain number of terms. So let's say we take first 10 terms and we add them, so we get an approximation of the sum itself. Obviously there will be an error, so we will see something very interesting about these harmonic alternating series. So this is just an example with some illustrations, so nothing special there with the alternating harmonic. Another example, so you see here -1 to power k, so this will be changing sign. This term here is responsible for changing of the sign. So when k is even, the sign will be plus. When k is odd, sign will be minus. Simple as that. Now the expression k plus 3 divided by k times k plus 1, so that's the main expression of the series, and this thing here is just -1 to power k is for the changing of the sign. So what we need to check is the term here, does it satisfy both conditions? So we need to compare two consecutive terms, and we need to compute the limit of the general term to see if it goes to 0. So one way to check the limit, so we can start with one or the other, doesn't matter, we need to check them both. One of the ways is to simply use techniques from Calc 1, so we divide by the highest power of the denominator, so 1 over k squared, upstairs and downstairs, and then we compute the limit. Here the limit is 0, so the first condition satisfied, that's nice. The other condition, we need to see if the next term is smaller than the current one. So what we can do, one of the techniques will be to just compute the ratio, because in this case it's not so obvious. In case of 1 over n, it was straightforward, we just write it down and we see it. But now, in this case, it's a little bit more complicated, so we compute the ratio, ak plus 1 divided by ak. If the ratio is smaller than 1, that means that ak plus 1 is smaller than ak, so the second condition would be satisfied. But we need to check a little bit. So we have ak plus 1 divided by ak, so we have double fraction here. We flip it. So we have this expression at the end. So k squared plus 4k divided by k squared plus 5k plus 6. So obviously the downstairs is bigger than the upstairs, so the ratio is smaller than 1. That means that ak plus 1 is smaller than ak, therefore the second condition is also satisfied. So now we have an alternating series and both conditions are satisfied, therefore by alternating series test, this alternating series is convergent. So you see, it's not so complicated to verify. Another alternating series, we see the sign that is changing, and the general term is k divided by k plus 1 plus 2. We compute the limit, we find the limit is 1, it's not 0. Oh, but we know that when the limit of the general term is not 0, that means by divergence test, the series is divergent. So you see here, by checking the limit of the general term, is the limit 0 or not? If the limit is not 0, then by divergence test, we conclude that the series is divergent. We remember that for the series to be convergent, we must have the general term going to 0, mandatory. If it doesn't, then the series is divergent by divergence test. So here I was in the process of trying to verify the two conditions of the alternating series test, because this series is alternating. But while verifying one of the conditions, I found out that the general term actually is not going to 0. It's going to 1. Therefore, by divergence test, I can say that this is divergent. An interesting thing is that in the case of alternating series, we can find an error on our approximation of the series. Obviously, how do we find approximation to the sum of the series? Well, we add certain number of terms. Let's say you add first 20 terms. So you get an approximation for the total sum. Now, in the case of alternating series that are convergent, obviously, those that are, we can actually find an approximation for the error. So the theorem here is very easy to actually apply. So we have the general term going to 0, the two consecutive terms are, the next term is decreasing. So now the alternating series is convergent by alternating series tests. That's fine. So that means that this series is equal to some number. Now we don't know what's the number. How can we find? Well, it's complicated, but we could find an approximation for the sum of the series. How? Well, we add certain number of terms. We can add first 10 terms, 20, 30, as many terms as we like. More terms we add, better approximation. Now, the result that is really special for the alternating series is that the error that I commit on finding the exact value, if I just add certain number of terms, let's say 10, the error is smaller than the absolute value of term number 11. So the next neglected term. So that's very useful to estimate an error. So this is very special for alternating series. It applies only on alternating series. So let's say here I have an alternating series. So 1 divided by k to power 4 with alternating sign. So if I compute this, obviously we can check the two conditions. 1 over k to power 4 goes to 0, and then here the next term is smaller than the previous. So that's straightforward. We still need to do it, but it's straightforward procedure. So now we can say that since we verified both conditions, this alternating series is convergent. Great. That means that when I add this thing, I will get a number. Now, obviously it's not easy to find that number. So let's say somebody tells us add first 40 terms, so 40th partial sum, using a computer. Obviously we are not going to do it by hand, and then estimate the error. So we will get an approximation for the sum, but also we are able to estimate the error. So if we use the computer and we add first 40 terms of the series, we get this number. So this is an approximation of the total sum. We still don't know what's the exact value, but we get an approximation. Now the question is, how good is this approximation? What's the error? Well, we don't know the exact error, but what we know is that error is smaller, so this here is error, is smaller than the next term in the series. So we have added 40 terms, so the next term is term 41. So here, this is changing sign, and the term is 1 over k to power 4. So adding 40 terms, error will be smaller than the next term in the series, which is term 41, so 1 over 41 to power 4, right? K to power 4, k is 41, and we get the number. So this means that this approximation here is good up to 6 digits probably, because the error here is smaller than 3.5 to power 10 minus 7. So that's what it means. So this number here is an approximation for the total sum, and the error is smaller than 3.54 times 10 to power minus 7. So that's the information that we have. So that's fantastic. We are able to estimate the error at the same time. Now the other type of question is, how many terms should we add in order for our approximation to have certain accuracy? So here, how many terms do I need to add in this series? So partial sum of Sn. So what is the number, n? Do I need to add 10 terms, 20, 5,000? How many terms should I add so that the error is smaller than 10 to power minus 10? So again, the formula is the error, the exact value which we don't know, minus the approximation. The error is smaller than the next neglected term. So here the term was 1 over k to power 4. So if we add first n pieces, then the next one is n plus 1. So we plug 1 over n plus 1 to power 4, and now we try to say this number here needs to be smaller than 10 to power minus 10, because that's the error they want. So let's solve this for n. So we shift this on the other side, because you have negative exponent, it will come up. This guy goes to the other side. Now we need to find n. So in this case, it's not too complicated. Sometimes we need to shoot in the numbers for n, but in this case, it's not so complicated. We can take fourth root on both sides. So we get this, and then we subtract 1. So we get n needs to be at least this number here. So we round up to the next whole number, because it's number of terms. So it will be 316 terms. So to guarantee that the error is smaller than 10 to power minus 10, we should add first 316 terms. Obviously, we are not going to do that, but that's how many terms we should add in order to guarantee that the error is smaller than 10 to power minus 10. So the number that we will get, if we add that, obviously using computer, we will get a number like this. So this means that 10 digits after the dot are correct. That's what it means, power 10 to power minus 10. So those are two types of questions, because for alternating series, we are able to determine if the series is convergent or not just by using the alternating series test. And if both conditions are satisfied, we know that series is convergent. So the next question could be, what's the error if I add first 7 terms? Well, the error is the absolute value of the term number 8. So the error is smaller than that. Or the question could be, how many terms should you add in order for the error to be 10 to power minus 5? So that could be another question. So here another series, alternating series, 1 over n factorial with alternating term. And the question is to find the sum that is correct to 3 decimal places. So we have some number, dot, and then the first 3 decimal places must be correct. What does it mean? The error term needs to contain 0.000 some number. So we need to have 3 zeros after the dot in our error. So first thing, since this is an alternating series, we check the 2 conditions, and in this case it's very easy, it's straightforward. This is the next term, which is equal to this, so it's obviously smaller than the term an, so term an is 1 over n factorial, so the first condition is satisfied, and this term obviously 1 over n factorial goes to 0 when n goes to infinity, so the limit is 0 obviously. So the verification of the conditions is straightforward in this case, but we still need to write it. So now we know that this alternating series here with the general term 1 over n factorial is a convergent alternating series, which means that this series here is equal to some number. We don't know the number, but we know that that number exists. So now what they want is to see what would be the sum that is correct to 3 decimal places. So the error should contain 0.000 some number. Okay, so what do? Well, we write out the expression in this case, and then we could start adding. That's cute, but when do we stop? Well, we need to stop at some point here when the next term is smaller than 10 to the power minus 3. So we could compute 1 over 24. Obviously, that's not smaller than 10 to the power minus 3. 10 to the power minus 3 is 1 over 1000, right? So obviously it's not this term, it's this term. So this is the term that will determine the error. So our error needs to be 10 to the power minus 3, and this term is the one that guarantees that. So that means that we need to add everybody before that. So all these terms here together, we add them, we will get a number. That number will have 3 digits that are correct. So the term number 7, if we compute, you see the error is smaller than this number here. So 1, 2, 3 zeros, because they have 3 decimal places. That means that we need to add everybody in front of that. So we add them. So this number here is an approximation of the total sum. And in this approximation, we know that these 3 numbers, 3, 6, and 8, are correct, because the error is, for them, is smaller than this number here with 3 zeros. So that's kind of straightforward process, and that's how we would apply the theorem regarding the error of the sum of alternating convergent alternating series. Another example of application for the results in using alternating series. So here we have an alternating series. So this is responsible for the change of sign, and this term is here your general term an. So your an will be 1 over 2 to the power n. So what we want is first to see if this series is convergent. So you can write out a couple of terms if you wish, it's fine. So to verify the 2 conditions, we identify the an. So we need to check if the general terms is going to 0. So limit of the general term when n goes to infinity is here 0, because this is 1 over 2 to the power n. So there's nothing special there. We know its limit is 0, so straightforward. Second condition is to check if the next term is smaller than the previous. So the current term is 1 over 2 to the power n. The next term is 1 over 2 to the power n plus 1. So 2 to the power n plus 1 is 2 to the power n times 2, obviously. So we just compare them. It's obvious that this is smaller than this, because this is actually 0.5 times the term. So this is smaller than this, so that's straightforward. Verification that the next term is smaller than the current. So since this is an alternating series, we check the both conditions, and then by alternating series test, we conclude that this series is convergent. So that's straightforward. Now the next question that we could ask is, what's the error if we add first 6 terms, for instance? So we had this 2, 3, 4, 5, 6. So if I add these 6 terms here, I will get S6. That's an approximation of the total sum, because we know this is a convergent series, which means that this series is equal to some number. I don't know what's the number. So I could get an approximation. If I add 6 terms, I'll get an approximation. More terms I add, better the approximation. But let's say just now I add 6 terms, I'll get an approximation. So what's the error? So error, we know that that's the sum that I don't know minus, let's say here S6, if I add first 6 terms. And we know that the error is smaller than the next term. So here the next term is 1 over 2 to the power 7. So if I compute quickly, what's this number here? So 2 to the power 7. And then 1 over, so this is approximately 0.0078. So I have 2 digits that are correct. So if I add these 6 terms here, I'll get an approximation for the total sum, and that approximation will have at least 2 digits that are correct. So that's one question. Another question could be, how many terms should I add in order to get certain precision? So let's say if I want to have errors smaller than, I don't know, 10 to the power minus 5, for instance. So how many terms? We should add for the error to be smaller than, so let's say 10 to the power minus 5. So in this situation, again, I don't know what's the n, so I'm looking for n. So error is the sum minus some Sn. I'm looking for this n. I don't know how many terms. But what I know, because this is a convergent alternating series, is that the error is smaller than the next term. So this is n, so it's n plus 1. Okay, so now they want to make sure that the error is smaller than 10 to the power minus 5. Okay, so this needs to be smaller than 10 to the power minus 5. So this way, I make sure that the error is smaller than 10 to the power minus 5. So I need to find n. So here I have 1 over 2 to the power n plus 1 needs to be smaller than 10 to the power minus 5. So 10 to the power minus 5 is this. Okay, so I just swap them, essentially. So I have 10 to the power minus 5. Everything is positive, huh? And this part here is 2n times 2. So I could either start shooting numbers here for n, try certain values, 5, 6, 7, so the first one that works is good, or since in this case it's possible to solve, so I'll have something like this. So how do I find n? What should we do? Well, maybe use the log. So this means ln of this is smaller than n ln2, which means that this thing here divided by ln2 so n needs to be the number that comes out of here, the first number greater than this, the first whole number. So if I just compute quickly to see what's happening, so I have 10 to the power 5 and then I divide it by 2 and then I take the log. and then I divide it by ln2. So the number that I get here is approximately 15.6. So n needs to be at least 16. Okay, so approximately that's what we do. We compute this number here. It gives us something. It is not a whole number, so we take the next whole number. So even if I had here 15.002, I will take 16. So you always take the next whole number. So n needs to be at least 16, which means I should add first 16 terms together in order for the approximation to guarantee that the error is smaller than 10 to the power minus 5. So that's very straightforward. It's a little bit of work, but it's quite simple. In the previous example, I recalculated and I just realized I made an error. The result that I got is actually 14.28, so that would be 15 terms instead of 16, because I recomputed, there was an error in computation from my side. So it would be actually n15 in the previous example. In this example, again, an easy one. So we have an alternating series. The term here is responsible for the change of sign, and 1 over radical n, that's our general term. So I just write out a couple of terms just to see how it looks like, but what matters is my general term. So we need to check the two conditions for alternating series, because this is one alternating series, and here it's straightforward again. The limit of the general term, well, it's 0, it's straightforward, there's nothing special to do. And the second condition is check that the next term is smaller than the current term. So the next term is here. It's obviously, so n plus 1 in radical downstairs is 1 over, is smaller than radical 1 over radical n. So that's straightforward, there's nothing special, we just need to write it out. So both conditions for alternating series test are satisfied. So by alternating series test, this alternating series is convergent. That means that this series is equal to some number. I don't know what's the number, but it's equal to a number. So let's say I would like to know, so there are two types of questions, is if I add first, let's say, 15 terms, what's the error? So what is the error for S15? So essentially I add first 15 terms, right? And I get a number. So that number is an approximation for the sum of the series. It's an approximation. So what's the error? So error is an absolute value. So it's the sum, which I don't know, minus S15 here. So what I know is, because this is alternating series and the result says the error is smaller than the next term. So the number 15 is the last one, so the next term is 16, so it will be this term here, because the general term is 1 over radical n. So the first 15 terms give me an error, so S15 gives me an approximation of this sum. So I add them by my calculator and I get the number. Now the error is smaller than this, so this is 1 over radical 4. 1 over 4, so this is 0.25. So if I add first 15 terms, my error is smaller than 0.25. So that's one type of question. Another type of question is, how many terms should I add in order for the error to be smaller than some number? So let's say, how many terms I need to add for the error to be smaller than, let's say, 10 to the power minus 4. So how many terms we need to add for the error most, so that's another expression, at most 10 to power, let's say, minus 4. So we want an error smaller than this. So how many terms? Obviously the goal is not to add 10 million of them, it's to add the minimum possible to respect this error. So the error, again, the formula is always the same. So the error is the sum, which we don't know, minus Sn, and this is smaller than the next guy with n plus 1. Here it will be radical n plus 1 downstairs. Okay, so this expression needs to be smaller than 10 to power minus 4. So this way the error is smaller than this, which is smaller than this, okay? The result from the theorem says the error is smaller than the next term, and we want that to be smaller than 10 to power minus 4. That way we are sure that everything is fine. So here now I have 1 over radical n plus 1 smaller than this. So obviously this is 1 over 10 to power 4, right? So what do? Well, we flip them. So I have 10 to power 4 smaller than radical n plus 1. So what do? To find n, well, we square both sides. So here 10 to power 4 squared smaller than this baby here. So 10 to power 4 squared is 10 to power 8. 8 minus 1 is smaller than n. So just to get a number, 10 to power 8 minus 1. So there's a lot of 9s. So this number here is 99. Okay. So n is the next guy. So that will be 10 to power 8, right? So I need this many terms in order to get an error that is smaller than 10 to power minus 4. So that's a lot of terms. That's what it means. So that's an example of application of the error expression on the alternating series, convergent alternating series.